Scott's Geography Notebook. Do you want to try saying it?
Da, da, da.
We want to talk about diffusion. And as we're talking about diffusion, we're really wanting to talk about it in terms of atmospheric optics. Okay, so what are we talking about as we're looking at atmospheric optics? What we really are paying most of our attention to is light that comes from the sun. So the first thing that we want to do is start to explore to understand a little bit more about the light from the sun. And previously, we've looked at other ways that we get all sorts of energy from the sun. The one thing that we do want to look at is the light energy from the sun. Now, that's radiation that's coming from the sun. It isn't the nasty kind of radiation. It's just light. And the light travels in the form of a wave. But this light from the sun is more than just that. So we'll talk about what that is in just a moment. Let's first start to understand what this diffusion is, because we seem to like to use these fancier words when we're talking about sciencey stuff sometimes. Well, diffusion really is just the scattering. Okay, and so when we're looking at the atmosphere, we have the light coming in from the sun, and the atmosphere is going to be scattering that light. Any number of things are going to be taking that energy from the sun and bumping it around, scattering it, making it so that it isn't going in a straight line. As a matter of fact, if we didn't have any scattering at all, then what we would have is we'd have our black sky and our sun out there, and that would be all. It would be almost like what the moon looks like with the stars around. But even the moon, we do get some atmospheric optics going on. So let's explore first this light that's coming from the sun. All right, so when light comes in from the sun, and I specify that it's from the sun because a lot of times light bulbs aren't necessarily going to work the same way. Okay? Light bulbs are made a little bit differently. The way that they radiate energy is going to be a little bit differently. But when we're looking at this light from the sun, then it's going to be, well, let's talk about the characteristics of what that is. If we could break this apart, and we do. If you remember on the cover of your chemistry book, or they put it on the cover of like almost every science magazine, they actually do break that light apart, and they have the white light going in, and then like it'll be all black on the background, and then they have all of these different colors coming out, right? So they actually do, and I could go through every color, but red, orange. Well, we do love colors, so why don't we? Okay, red, orange, yellow, green. And right, it's got little stripes. Now, this is not having to do with diffusion. This is having to do with refraction, with bending and everything else like that. But what this little picture that we see on our science books demonstrates to us is that this light that we have coming in from the sun isn't just white light. Okay? It really is a mix of the entire color spectrum. So if we could, what we would do is we would break these guys apart. Okay? And that's what the prism does, but let's not go there yet, because that's just going to confuse us. Okay, so white light is actually a mix of all of these different colors. So the white light from the sun, the mix of all. Okay, of these guys. So we have our red, our orange, our yellow. We've got pens falling on the ground. Make sure that we don't need those later on. Yeah. Okay, green. There we go. Green, red, orange, yellow, green, blue. Oh, that's a purple and a half. No, okay. Purple. Okay, so white light really is this combination of all of these. As we're looking at these different colors in the color spectrum, they all come through at a different frequency. Remember that the white light is traveling along, and we say that it's a radiation, or it's energy traveling in the form of a wave, right? And so this white light, right, all together, we call all of the light that's coming from the sun, that fits on the shortwave radiation. So we're going to say that this is all short wave. Light energy is shortwave, but if we were to look at these guys, they all travel at a slightly different frequency, meaning that as a wave, the highs and the lows and the highs and the lows are going to be at a little bit different rate. Okay, so what do we know? These guys over here are a little bit longer It's all short waves. These are a little bit longer. These guys are a little bit shorter. Okay. So if we could take this white light and see it as wavelengths, what we would have is we would have this red, right? So from peak to peak, or trough to trough, right? It's going to be a longer wavelength. And then the orange is going to be a little bit shorter, right? Peak to peak, trough to trough, okay? Shorter. And then yellow is going to just ruin my yellow here, I think. Okay, it fits right in there. And what's next? Green. Oh, these wavelengths are getting smaller, right? And they're all starting in the same spot, so I don't know what happens to that. We have green already. Blue. I'll get blue in here. It's about the same as the green, but not really. Okay, hopefully you get the idea. Okay, so when we are looking at these, it goes on, well, okay, you get the idea. So when we're looking at this white light really is this combination of all of these different wavelengths. Okay? So this is kind of important to think about, both in diffusion or scattering the light, right? Because why? Okay, because some particles are able to scatter just the blue, or just some of the blue. Okay, oxygen and nitrogen. We'll talk about those in just a bit. Okay, or in another video. Salt particles, water droplets. Those are going to be reacting differently to a lot of these different guys. Okay? So we'll get into that in just a moment. But understanding that the white light that comes to us from the sun is really this combination of all of the different colors. All right? Now, I talked a little bit about it just there for a moment, but when we have the light, what is going to be scattering it? What's going to be causing it to go in different places? Well, it all depends on, dependent on the size, right? The size of the particle. Okay, now there are a number of different things that we have out there. The very first thing that we'll start to talk about in another video is going to be the actual atoms or molecules, the gases that we have. So atmospheric gases, namely oxygen and nitrogen, O2 and N2. Other things are going to be doing this as well. We're going to have salt particles, maybe in the oceans that are going to be flying around there. We may have dust. We may have ash, right? If there's a fire. If it's dusty, for example, Central Valley in the middle of summer, we haven't had rain forever. We might have some dust in the air. If we're near volcanic eruption, then we have aerosols or pyroclastics. Okay? Those are just going to be some of the ashes coming up out of that volcano. Then the other thing that we see a lot of is going to be water droplets. Either individually as water droplets or all together as clouds and haze. Okay? All these are going to be water as a liquid suspended in the air, but it's going to be interacting in a number of different ways. We've got some other videos lined up to kind of talk a little bit about how each one of these work. Okay. So what do we know? We know that the white light that's coming from the sun is broken all apart. Some items, depending on the size of the particle, it might break it all apart, right? The water droplets, you get the white light coming in, clouds look white because of that. You get other things like those atmospheric gases, it might be selective about what it does with that. So it might choose, hey, I'm only going to mess with the blue rays that are coming through and scatter those around just a little bit. So the size of the particle is going to be influencing whether it is altogether scattering or if it is selectively scattering.